Again, we have a minor concept of resonance. Resonance is the process whereby a state whereby one object oscillates as a result of impulses of another object. You see, so there is a matching of frequencies, that another object, external object, oscillates at a certain frequency equal to the natural frequency of the other, so they tend as if they oscillate together, but the other is oscillating because another external body is oscillating. Hii ni very very practical kwenye radio. Unapokuwa na antenna, ile antenna ina receive frequencies za stations tofauti tofauti. So unapoitune radio yako kwamba umeiweka kwenye namba fulani ya frequency, it means ifanye resonance na frequencies zinazokuja za kituo ambacho kitakuja na hizo frequency. Kwa kitakachotokea hapo, resonance itatokea kati ya radio yako as a result of impulses received from the oscillations of the channel au station frequencies ambazo umeziweka. Kwa ni practical application. So resonance usually occurs when the reactance of the inductor is equal to the reactance of the capacitor. Okay, when the reactance of the inductor is equal to the reactance of the capacitor. Okay, as you can see that, I know you know this, that if you see clearly, both X and L depend on frequency, therefore current depends on frequency F of supply. Frequency of note, which causes root mean square current to be maximum for given value of voltage, resistance, inductance and capacitance, is called the resonant frequency. Okay, so resonant frequency is the frequency F naught which causes current to be maximum. Okay, it causes current to be maximum. So there is a certain value of frequency in which current will be maximized in the RLC series circuit. So that frequency we get it by equating, because at that state is when the XL is equal to the XC. So we maximize current by minimizing the impedance. So impedance will be minimum when these two have matched, so that this value is 0. Okay, this value is 0. That's when we will maximize our current, because our issue is to try to minimize this to as small as possible. The limit is 0 when this value is 0. So you can put the reactance there of the capacitor, reactance of the inductor, capacitor. Then our interest is to make F naught the subject, and that F naught, that will be the formula to get the resonant frequency. Therefore at resonance XL is equal to XC. Ipo kama resistance matching fulani hivi, lakini sio resistance matching. Kwa ukumbuke tu hicho kitu, kwamba also at that stage, kama hizi ziko tu, kama resistance zao zinakuwa sawa, hata voltage across them zinakuwa sawa. This means that resonance, the peak values VL0 and VC0 are equal, and that since they are out of phase, you remember I said V ya huyu ipo kwenye sine, kwenye cosine, hii ya huku ipo kwenye sine. As you remember, V ya huyu ipo kwenye sine, V ya inductor ipo kwenye cosine. Ni V ya inductor ipo kwenye cosine, ni V ya capacitor ipo kwenye sine. They are out of phase by pi radians, as you remember. At every instant, the total potential difference across inductor na capacitor is 0. Okay, at every instant at resonance is 0, because they cancel each other. They are equal and opposite, so they cancel each other. They are equal and opposite, so they cancel each other. So it follows therefore at resonance the applied potential difference is equal to the potential difference across the resistor only. If this value is over, even the impedance will be equal to the resistance only. Even the voltage that will be supplied is equal to only the resistance, the voltage across the resistor is what it means here. So it is in phase with the current. So as you can see, graphical representations there are cancellations, and hence superposition principles. So these are the conditions at resonance. This sometimes they ask, so you can pass through this here. And here we have what we call Q factor, which is the quality factor of the circuit, and is given by the value of reactance of the inductor, the ratio of the reactance of the inductor to the resistance. Okay, so it's just the Q factor. It's not very important, but it's nice to know. Okay, circuit with high Q factor has high resonance. So it's a practical application that if you want to measure how this radio, for instance, the maximum or highest resonance, you want to maximize the resonance that it can achieve, is by improving the Q factor or the quality factor, the quality of the instrument. Application, as I have said, you can see here, it's just the same in the radio waves. Here we have alternating current versus DC. There are things which can be read, so they are here for you. You can pass through these differences here, and you can see for yourself. They are easy, and everything is given here for you to read. It's easy to understand. They ask these questions in the exams, so there are things that you can never afford to miss marks. Our target is next. How do I do this? Remember, books to use. Make sure you solve a lot of questions from Rogers, Mancaster, and from Nelcon. These are the books that are very rich in this current electricity topic. If you solve so many questions in this book, be sure to pass questions of current electricity. As usual, don't forget the review. Pass through as many questions as possible, as many years as you can. Visit but not prioritize Chand. Chand is not very useful here. You can pass it for practice, but do not prioritize it. Most questions solved from Nelcon and Rogers, Mancaster. Carry your knowledge. It is important in practicals. Remember, this topic has practical part in your nectar. So remember to carry all this knowledge and be able to translate it into practicals. So whenever you are dealing with practicals, remember to recall all this knowledge that you have gained in the theory. It will be very helpful. As usual, it carries 20 marks. It has 2 questions in section B. Sometimes they put alternating current in the questions of paper 2 in the part of electromagnetism, so it's not a big deal. So it has minimum contribution of 20 marks at least for paper 1. Otherwise, I wish you all the best. I thank you for your attention.